You're good.
Okay, let's get started. Good afternoon, everyone. For those who don't know me, my name is Dong Lin. I'm the new co-host of the summer colloquium. Many thanks to Li Yin Chen for her service in previous years, and it's my pleasure to relay the efforts from her. Today, our speaker is Professor Xian Lu from Clemson University. Dr. Lu is an associate professor in the Department of Physics and Astronomy, and her research interests focus on neutral dynamics and space weather. She has been leading multiple NSF and NASA grants, including NSF Korea, NSF Answers, and NASA GIGI. She has received Rising Star in Discovery and the Dean's Professorship Awards from Clemson University. And today she will talk about storm time atmosphere ionosphere magnetosphere coupling with data assimilation. So, Xian, now's your time.
Okay. Thank you very much, Don, for the introduction and the invitation to give this talk. So I'm very glad to have this opportunity to present our recent work and have discussion with experts at HAO and from other institutions as well. I presented some of the work at CEDAR, which was just 2 weeks ago. So I apologize if some of you see repeat results in this talk, but you may get new points out of it, hopefully. For this work, we focus on storm time atmosphere, ionosphere, and magnetosphere coupling enabled by data assimilation. So the storm event we chose is St. Patrick's Day storm on March 17th, 2015. So this is a very famous storm event, and it has attracted a lot of attentions, as we probably all know. So there are a lot of papers talking about the storm impacts all the way from equator, such as on scintillation on the EIAs, and also to high latitudes, such as the TEC such as on the TEC maps. Also, there is a special section in GGR Space Physics organized by Dr. Shunrong Zhang. They collected a lot of papers covering the storm impacts all the way from magnetospheric forcings for this event and to the high latitude subaurora and the mid latitude responses all the way to low latitude, such as PPEF and the DDEF impacts from this storm. So this is a storm case. As we can see, the DST indices go all the way to negative 200, even more negative than that, and the maximum KP index goes to 8. And also the AE index is pretty high for this event. The reason why we chose to revisit this case, initially it was motivated by a FPI observations, FAVOR-Pro interferometer observations at Eagle, Alaska. So my colleague, Professor John Merriweather, came to me with his neutral vertical wind observations from the FPI, which showed very strong upwelling, upward vertical winds, neutral vertical winds around 9 UT, and also from other nearby measurements, such as those from Pfizer, which is in Poker Flat ISI observations. There are also some interesting phenomena, such as the increase of the ion and the electron temperatures, and also increase of the neutral temperatures. So the question that we wanna understand and answer first is whether the IT model, ionosphere thermosphere model, can simulate such a localized IT system response to the intense storm. And if we can, then we can use the model to better quantify and better understand the underlying physical processes. So for this particular event, the data coverage is actually relatively good. The phase observations have pretty nice electric ion drift observations, which can be used to derive electric fields. So this is the electric fields and ion drifts from phase observations. And we also run AMI, and AMI captures the trend of the electric fields and ion drifts pretty well. From the results we have, it seems like the magnitude of AMI tends to still underestimate the phase observations, the local observations. And also for this event, the aurora activities are very dynamic. Around 9:30, it starts with a PVI move equatorward, followed by aurora surges, streamers, and around 9, right here, around 9 UT, where we see the very strong upwelling in neutral vertical winds. Around the Alaska section, there are very strong aurora activity, strong aurora activities in the Alaska section. So we know that from the emission, aurora emission, people can derive energy flux and the mean energy, which are two important inputs, aurora parameters that can be used by the IT model to drive the model as high latitude inputs. From this perspective, for this particular event, we do have nice characterization of the magnetospheric forcings in terms of aurora and also electric field observations. So because of this, then the motivation is if we can use the data assimilation to better constrain the high latitude drivers. In this case, one is aurora maps and the other one is ion convection maps. If we can do it, so then locally maybe the structures and distribution of the energy deposition would be more realistic coming from this data assimilation, and the sources also have very good data coverage for this event. And if you use this to drive TIE TCM, so what would be interesting is whether the model can reproduce the observed IT responses, such as electron density, ion temperature, electron temperature, because we do have observations from Pfizer, and also TEC observations in terms of the global response. And we have GNSS observations that can help us to compare, and also the FBI observations of neutral wind and neutral temperature. But we do have other data sets. We haven't compared the results yet, but this could be also considered in the future studies. So then the model, to some extent, is kind of like constrained end to end. So we want to use more realistic inputs, drivers, and say whether we can go all the way using the physics model and propagate that driver and to get to these observables, and we can establish the link in between. So in terms of the data assimilation framework, we collaborated with a few of our math colleagues at Clemson University, and they recommended a multi-resolution Gaussian process model, so-called Lattice Kriging. I think initially it was proposed by Dr. Nishka, and Dr. Nishka used to be also working at NCAR. So this data assimilation model basically can take in irregular observations, and assuming the process is a Gaussian process, and then the fields can be written as mean plus deviation and also the error term. So mean, in this case, we can actually use the background model. Such as for aurora, we have aurora empirical models. And the deviation part, which is GX, deviation actually can be physical, and it is physical. So GX, X is the location of the observations. So Gx actually means the spatial distribution from the physical variables. So observations, to some extent, can help us to to estimate mean, standard deviation, and also covariances of the fields. And by decompose this deviation term, which maybe more correct term would be deviation. Deviation term to the basis function, which is R in this case, and by assign the covariance matrix. And in this case, we're still given, this matrix is still given. It's not based on observation yet. Then the observations can be used to estimate two factors. So one is D hat, the other one is C hat. So D hat is used to scale up the means. As you can see, D is right here, and Z is the mean background model. But usually mean background model tends to, sometimes even tends to underestimate the overall levels of, for example, aurora. So we do need a scaling factor here, and this can be estimated from observations. Why here is the observations. Then also another coefficient is C hat. So C hat is coefficients of the basis functions. So those coefficients, because we project it into basis function and use it to represent the deviation term. So the C hat in the end can be also estimated from the observation. And then once we know these two coefficients, then the risk construction of the field can be done at all locations. So basically X then can be at any location, and it can be regular grids, and also it can be multi-level, because when we locate the basis functions, it can be actually, we can actually do multi-levels and do different resolutions in terms of the basis functions to realize the multi-resolution data assimilation. So this is the basic principle of this data assimilation model. And this is the, as I mentioned, this is the basis function maps. And so this is one example of using 3 different data inputs. One is from satellite DMSP SUSI, and one is from THEMIS, ground-based, THEMIS ASIs, and also the empiric model. So this model we used the Jones model, which is based on the statistical study of the SUSI historical data, and is KP driven. Because we do have control of the location and distribution of the basis functions, so we can actually assimilate from low to middle, and to high resolutions, which naturally can differentiate the scales of aurora and also for electric fields. So if we compare the arrow analysis, so this arrow is root mean square arrow, which means that is that's the difference between the assimilation results with the observations. So it's the root mean square arrow, and you can see if we go to lower resolution, the arrow decrease, and if we go to multi-level, such as this, it can even decrease. And one more big advantage of multi-level is the computational efficiency. Because more than often, as you can see from these examples, the observations are not global. And also, especially for electric fields, if we talk about Solar data used for electric field assimilation and maybe some scattered ISR observations, actually observation locations are still limited. It's not global. So if we actually can line this high resolution to the regions where we have observations, and other regions we can actually relax out, not using that high resolution. And by doing this way, it can efficiently decrease the computational time by a factor of maybe 6 to 8. So which can actually make this data assimilation more affordable in real application. So this is the example for aurora, and Initially, the lattice Kriging is proposed to do the scalar fields assimilation, and we did a little bit of extension to use it for a data assimilation of vector fields. So the idea is we assume the electric field is curve-free, then we can then it can written as the gradient of electrical potential, and we still starts from the electrical basis function. It starts from the electrical potential, starts from phi, but we know that observations are actually usually is the line of sight observations of ion drifts or line of sight observations of the electric field. So we do need to kind of like manipulate a little bit in order to assimilate the observables, which is line of sight variables. So, but this actually is quite straightforward, because if we start from the electric potential, we do the gradients, and then we can, so here is a vector, but we can project it into line of sight direction. And in the end, we can get the line of sight basis functions for line of sight electric fields. And we do a simulation based on these, but the coefficients are the same, because our goal is to estimate the coefficients C in this case, but you can see that they do not change. So basically, then we can also using just by converting the basis functions a little bit, we can still estimate the coefficients and then project it back and get the reconstruction for the global fields. So this is how we extend it to the vector fields, and it turns out to be quite successful in terms of data assimilation of electric fields. So this, you can say, compared with the background model, this is a root mean square error comparison. Background model, in this case, is Weimar, like shown here. Compared with the Weimar model, if we use 8 degree, the error is already decreased by half. But if we go to higher resolution, we can capture more details of the observational fields. And if you remember the figure I showed previously, if you go to multi-level, the arrow is actually even smaller. And this can be also seen by the comparison with Pfizer observations. So in this case, the black line is Pfizer observations, and the red line is our assimilation results. So I would say, in generally, those two match very well, which is kind of expected, because Pfizer is used as a independent point into the data assimilation. But sometimes there are still disagreements. For example, like this, and we suspect this is maybe because of the dominance of the solver-down data, which we didn't really say if the solver-down data is very close, we do not use that information. We actually kept pretty much all the available observations. So sometimes it may be dominated by the solver-down background model. But overall, I think the data assimilation is pretty good and well captured the temporal variabilities of the electric fields. And as you can see from the comparisons of the ion convection patterns, and you can also see some localized structures like vortices are observed compared with the very relatively smooth pattern from the empirical electric fields, from the empirical models. Okay, so this actually, we published this paper, and Haonan also made the codes available and share it through the GitHub. So if you are interested, please feel free to contact Haonan or me and ask him for more details of the simulation codes. All right, so this is the data simulation of aurora on the right-hand side, and electric fields for the St. Patrick's Day in 2015 case. And if you remember, yeah, sorry, I didn't point it out. So the electric field, there is a very interesting phenomenon is around 9:30 UT. Pfizer observed a very strong northward electric fields corresponding to a westward ion drifts to an order of minus 1800 meter per second. Pretty strong electric field around 9:30. So actually you can see that if you see the assimilation results, this is right here. So that one is actually incorporated and is showing in the map. And you can see compared with the empirical maps, there are some more details in the structure. And at the same time, the local peaks also changed, and that's modulated by the data information. So to some extent, if we have more data, this map would be more realistically approaching the reality. And for the aurora, similar stories. We say it's because those are from, for example, I bet this is from THEMIS observations, and this might be from SUSI. So the observations sometimes show quite a bit of structures in terms of this kind of like large scale and smooth patterns. But another feature I don't want to point out is the magnitude of energy flux of aurora actually is much higher than the empirical model, and this is number flux is much higher than the empirical model. So it's been significantly elevated, but we do find out a issue that may need to talk to HAO people is we find out that TIE GCM cannot fully cooperate for example, the aurora precipitation from THEMIS ASI. So for this event, if we use the original aurora observations, the TEC is way higher than the observations. So as a trade-off, we cut off by half. So the observations is decreased to half, then the model can better cooperate. So I think this may be some issue that modelers and also experimentalists, data people need to talk and say how to resolve this discrepancy But at this point, what we did is we actually cut it to half, and then the TC and the electron density better matches observations and doesn't mess up other things as well. So that is what we tried at the current stage. Then we use then we did several model runs. So one model run that we used empirical models, Aurora model, and empirical electric fields, and the assimilation run is we use both assimilated electric fields and Aurora to drive the TIE GCM. And this is the comparison between the Pfizer observations and the outputs from an assimilation run and outputs from the default run, which use empirical drivers. And as you can see, many things have been improved. For example, the electron density. We say the kind of like secondary peak around maybe in the E region and the lower F region, which is not seen in the default one, starts to emerge in the assimilation one. And another interesting, really interesting thing is from Pfizer observations around 9:30. So it's the time that I pointed out earlier. The EY shows a very strong increase around 9:30. the TI from observations actually also show a significant elevation. And this is seen in the model simulation, even though the altitudinal distribution is not exactly the same, but the timing and the general magnitudes are pretty good. But all these are missing in the default one. And the fourth row shows the vertical neutral winds. Since this is the motivation, so we also paid quite a bit of attention. From the default one, we do not have significant winds pumping up at all. But from the assimilation one, we are able to actually get the vertical winds as large as like 40 meter per second, 50 meter per second, but not all the way to say 100 meter per second or 200 meter per second as observed by the FPI. So there are two possible reasons. One may be from the observational side, and the other one may be from the modeling side. And we don't know the answer exactly, but from models, we know TIE-GSM is hydrostatic, even though the strong vertical winds does last for like 1 hour, but still we're not very sure about whether non-hydrostatic processes even play a role, or maybe some other physics play a role in terms of the vertical wind measurements. And also in terms of the data observation itself. So some people are talking about contamination from aurora or some other issues. So in this case, I mean, the take-home message is the vertical wind is much stronger, and we believe this can be real, can be achieved. And yeah, so then in order to better understand which factor drives the improvement of the simulation, we can do the control runs. And because we have two different choices for aurora and two different choices for electric fields, one is empirical and one is a simulation. So it's naturally that we would have 4 different runs by using either empirical or assimilated maps for these 2 variables. And we come up with 4 runs. Run 1, both are empirical. Run 4, both are simulated. Run 2, aurora is assimilated. Electric field is empirical. And run 4, aurora is empirical. Electric field is assimilated. So then we can differentiate which is more important to generate the observations that we have. So this is TI. This is TI. For TI, assimilation of aurora doesn't impact too much. So at least from the physics that's in TIE-GSM, we can say the TI is mostly coming from the electric fields likely by the frictional heating in this case, and it's quite instantaneous. Every time we see the increase of electric fields, instantaneously TI would increase. But I also want to point out one thing is the difference between observation and simulation is from observations, you can say those impulses, the timing, it's pretty matching with the simulation matching with observations, but we do also say the differences. For example, the increase of TI sometimes does not go all the way below 200 kilometers, which is pretty weak. But from the modeling, we go all the way down. So I think this maybe is because how the TI is calculated in the model itself. Then how about TE? So TE, even though by the first glance, even though electric field again is the dominant controlling factor, but aurora, if we use the assimilated aurora, and we do know that from data assimilation this time periods, aurora will significantly enhanced because we used observations to drive the model. So aurora also play roles in this case, and you can see especially the temperature would increase in the range of 200 to 300 kilometer range. But electric field also it's quite important in terms of the general increase of electron density in this case. For electron density, then aurora is more important, and because aurora impacts the ionization rates and further affects the electron density, the production of electrons. So as you can see, if when the aurora assimilation is not implemented, which is for round 1 and round 3, we don't have this kind of like the enhancement of the electron density below 200 kilometers, and in the E region, and the secondary peaks are missing. But once we have the strong aurora precipitation in the model, we can actually simulate and see this better in this case. And for vertical neutral vertical winds, if we have the electric fields assimilated, then the average winds are actually more shows more variabilities, more temporal variabilities, instead of this is kind of like more long-term change, like few hours, several hours long. I mean, relatively slower change of the vertical winds, because now the electric fields really change really rapidly, as they shown by the observations. So you can say the response of the neutral is also can actually catch up this, even though neutral do have some inertial, but we see these neutral winds can actually show short-term variabilities and enhancement magnitudes in the F region. But for the FPI region, for the FPI to observe the significant neutral vertical winds, we do say that aurora is also important. And the part of the reason is aurora we have to have strong aurora in order to increase the ionization rate and increase the Joule heating at lower altitudes. And then we have this enhancement of the Joule heating, then can cause the local heating, then generate the upwelling above this range, which corresponds to the vertical winds here. So to vertical winds, especially at lower altitudes, we think both electric fields and aurora precipitation are important in this case. So we also compared integrated Joule heating, so high integrated Joule heating, and the upper figure shows the integrated Joule heating at Poker Flat, and not surprisingly, the integrated Joule heating at the Poker Flat is much stronger. So to some extent, it means that empirical model does not capture the localized energy deposition at Poker Flat, which is better constrained by the incorporation of the realistic drivers. And another thing we compare is the maximum integrated Joule heating in the region 50-degree poleward. And the reason to compare these is actually we're trying to say whether globally, whether the data assimilation will lead to kind of like unrealistic enhancement globally. But it turns out it might not be the case, because in terms of the maximum value, you can see it's more comparable. And except the data assimilation gives more temporal changes than the smooth pattern of the empirical thing, but the magnitude are more comparable. So to some extent, the data assimilation kind of like modulates the spatial distribution of the energy deposition instead of, say, globally averaging every location. So that's not happening. And then we would imagine that if we have better data constraint, which can give us more realistic spatial structure of aurora and electric fields, then that will be kind of like ideal to drive IT models to better understand the space weather impacts. So this may call for the importance of data coverage and observations from satellites, missions, future satellite missions, and also ground-based network observations as well. All right, so the next thing we compare is the TEC, which is more global. So those are 4 runs, and this figure shows the GNSS TEC, TEC observation. And I want to draw your attention here, which is aurora oval, and sometimes the enhancement of Alaska section because of the aurora surges happening right there, and you can compare. Yeah, so if we stop here and maybe, yeah, right here. So I would say, so here we see the increases, and around the aurora oval, we see that. In the empirical runs, it's missing basically. But from the data assimilation, I think it's more realistic. And also here we see the increases as well. So then we also checked the vertical winds, because vertical winds can be used to look at the TADs and higher frequency, smaller scale waves. So those are the 4 runs of vertical winds. And you can see here, so which is around, yes, around 9:30. Around 9:30, this here corresponds to the strong Joule heating from the strong electric fields. And another time that we also have significant response in the neutral wind is around, it's after 9 UT. So because after 9 UT, electric fields haven't still maintain a considerable level, but at the same time, aurora catch up. So then you can say it can generate a lot of wave propagating to the low latitudes. But compared with empirical run, which is left-hand side, and this is 250 kilometers, and this is 550 kilometers. So compared with the empirical drivers, the TADs, first of all, the magnitudes tend to be weaker. Second of all, the coverage, the extension of the waves seems to be more limited in the empirical run, but it tends to be able to reach further and lower latitudes if we can actually use the data assimilation as the driver. So from this, then we can say that, okay, then from different runs, because the variabilities seems to be quite different. The temporal variabilities seems to show more short-term stuff coming from the assimilation. And the second thing is, as you can say from these. So spatially we also kind of like expect more variabilities spatially. So then I think interesting thing to compare is then what kind of the variability we can see from different runs. So the first row shows the longitudinal standard deviation. So what we did is, for example, this circle the longitudes, we take the standard deviations. Then we can have that as a function of latitudes and also local time. And you can say that when the assimilation is used, the variability is much enhanced, and also some much enhanced, and also sometime from the empirical it does not show too much, but it is there in the simulation run. Then we take average of this in terms of time. So this is temporal mean of A1 to D1. So after we take temporal mean, then you can say, first of all, the high latitudes, the variability increased by a factor of 1.5-ish. But for low latitudes, the increase can be stronger, like a factor of 2, as you can also see. So you can see these are actually TAD. I believe they're actually TAD signals. They extend to lower latitudes, and they show a lot of variabilities in terms of time in this case. And second thing we calculated is so-called temporal variability. So which we did is at each location, which is long and lat, we calculate the temporal variability. And the temporal variability then goes with location, and also is much enhanced because of the assimilation. And if you compare the longitudinal mean, also it's zonal mean, so take the zonal mean of this, then even at high latitudes, the variability can increase by a factor of 2, and also sometimes even 3 for the lower latitudes in this case. So to some extent, we say that more scales are included, and a larger dynamic range, more scales, and the larger variabilities can be enabled if we consider the realistic drivers to drive the IT model. And the last thing we did is we kind of like want to say whether small scale things have feedback into large scale things such as zonal means. And in this case, this is not technically, it's not exact comparison because R1 is using empirical, even though empirical does to some extent is large scale things. But to be more exact, what we should do is we should use the large scale data assimilation, which we haven't done. So in this case, we used empirical model to represent large scale, only consider large scale things. But R4, as you can see, because R4 does include more scale things in it. So if we compare the zonal means, you can say different runs, they can be very, very different. And the differences sometimes is significant. Zonal mean meridional wind sometimes is even like orders of 100 meter per second difference, which is also quite interesting. And the vertical winds, is more, it's more smaller scale, smaller circulations. In terms of say large, you can say here, for example, is zonal mean. This is down welding, this up welding, but from the simulation run, we can say actually it can be more sketchy, and can involve smaller scale circulation locally. But for neutral temperature, is a net. Pretty much is a net temperature increase if we use the assimilation results. So I think we should replace this one. If we should place R1 with the large scale assimilation pattern to replace R1 and do the comparison. I think that's more robust. But this, to some extent, is also has some implication as well. So to summarize, data assimilation assists the simulation of localized energy deposition and IT responses to severe geomagnetic storms. So the responses can be more dynamic than being simulated before if we use default runs, and we see richer scales, stronger variability, and a larger dynamic range, such as for neutral vertical winds. And this is a factor of this. And the locally Joule heating can be significantly enhanced, but globally or regionally, it can maintain similar level. So it's more like a redistribution of energy deposition instead of overall elevation. And we also kind of like foresee the great impacts of small scale and short-term processes on zonal means and also on large-scale patterns are quite significant. So for IT models, we think data assimilation can maybe help us to learn new things, to learn something new and better simulation. Then from this perspective, the data and observations are quite important. And also we are aware of the community efforts, great efforts in developing the fully coupled model like MAGE, which can also capture more realistic dynamics, electrodynamics processes, and that's also a very good. And this project is supported by several NASA and NSF grants, which I don't need to mention them actually. All right, yeah. So that's all. Thank you.
Thank you, Xian. Okay, let's move on to Q&A time. That's very nice talk. Does anyone have any questions for Xian? Just raise your hand or directly unmute yourself. Well, okay, Han Li, please go ahead.
Hi, Xian. Thanks for the nice talk. I have a question on the slide where you show the integrated Joule heating, where you compared the blue and the red curves, and yeah, some like between 9 and 10, you do see a enhanced enhanced Joule heating from the simulation of both E and I, and but also at between 6 and 7, the red actually is lower. Is that because the realistic electric field is suppressed when you assimilate the observations?
No. No, the assimilation of electric field is stronger. I mean the difference between the blue and the red curve are aurora, because both are. I mean, for these two rounds, electric fields are both assimilated, but for red line, aurora is assimilated, but for blue line, aurora is empirical.
So you mean the empirical aurora is actually stronger?
Yes.
Okay.
Could be. I think from the observation 6:30, the aurora is pretty weak. We didn't see too much aurora there.
But maybe I misunderstood this. In the blue line, you said the empirical E.
Blue line is aurora empirical electric field.
Oh, okay. I see. I read the other one. Okay, yeah. I see. Got it. Thanks.
Okay.
Okay. Anyone else? Okay, Wenbin, please go ahead.
Yeah, nice talk. So I have a question. You talk about you have to reduce aurora by half. That's you reduce number flux, or the mean energy, or both, or
we reduced energy flux and keep the mean energy as it is.
So
that will like decrease the number of flux by half.
okay. So you compare with TEC, that's a local in the region of your observation. That's right. Or
Both,
right?
kind of like both. Right. I think the first thing we compared is the local observation of NE. Seems like if we use the full energy flux, the NE is too high for poker flat, and TEC is also high. So then we kind of like cut it half and make it more reasonable for the simulation.
Okay, thank you.
Yeah. I mean, yeah, I think maybe we should sit down and talk about it.
Yeah.
Issue.
Yeah, actually, I have a follow-up question on that. So could it be related to the background, the neutral background that affect the TEC results, rather than because of the precipitation?
Could be, but would it be that? I mean, would it be that much impacts? Because if we use the full energy flux, I think NE can be higher by a factor of 5, or sometimes even order of magnitude higher, 10, 5 to 10. I think that's quite significant. Then another question is that if it's mean background, neutral background, then how can we judge that? I mean, what can we say whether it's because of this and because of neutral? Do you have any clue?
Well, I'm sorry. The thing probably we need to benchmark from some other aspects rather than the precipitation and the TEC themselves. After all, the IT system is very complex. But yeah, I agree. Probably we should sit together and chat about this more.
Yes.
Okay, cool.
Yeah.
Yes. Okay, let's see if anyone else got questions. Oh, Qingyu, please go ahead.
So have you compared the differential TEC as certain regions, say Alaska regions?
We haven't we haven't done that. But
Yeah,
that's a good suggestion. Yeah. But I would say for this event, even for the absolute TEC, the enhancement is pretty clear. It's very obvious in the Aurora region. And if we compare different TEC, you will still see this very distinct thing in different TEC as well. But you may get rid of this in the different TEC, right? Yeah.
Right. Yeah.
Yeah.
Oh, Hallie again.
Yeah, Shane, I have another question. So has the result here been compared with, say, Amy? I was wondering if if the differences are due to assimilation or due to resolution or both.
Yes, I think initially we used Amy, but we cannot get this. I mean, if we go to these, you can see Amy. Amy still underestimates the magnitude. So I think the first try of running the model is we used Amy as the driver, but it does not actually quite get there in terms of, especially in terms of the neutral vertical winds. So then what we tried is a couple of years ago, then we simply add Pfizer observations in a box, like 3 × 7 box locally in poker flat. Then you would imagine there is a boundary, artificial boundary there. But that model 1 actually can give us a very strong neutral vertical winds as large as 150, 200 meters per second. But I would say that's probably drive the model all the way to the limit already. that involves very, very localized and extreme energy deposition. That but it's not quite realistic in terms of the driver itself. So then we kind of start to think about how to incorporate local observations more coherently using the data assimilation in this case.
So the resolution does play an important role.
Oh, you mean the data assimilation resolution?
Yeah.
Oh, yeah.
Yeah.
Yes, of course.
Okay.
Yeah.
Thanks.
Yeah, I also have a follow-up question. So for that data simulation, is that the ensemble based, and computationally, how much more expensive is that compared to the standard TCM run?
I think it's comparable.
Comparable?
I mean, yeah, I think a data assimilation itself, because TI-HSM use these as external inputs, right? So basically, you're gonna compare these aurora maps and electric fields as external inputs and use it to drive the TI-HSM. So once that is ready, I think that's comparable with you use AMI.
Okay.
Or other. Yeah.
Okay, let's see. Any more questions? Okay. Looks like we have already got a very great discussion. Let's give applause to Xian for her great presentation. Okay, thank you everyone. Thank you for joining the colloquium today.
Okay, thank you.